Welcome to Chapter 1 of Introduction to Quantum Computing. Quantum computing attracts a great deal of attention and also a great deal of exaggeration. This chapter builds an honest foundation. We ask which problems genuinely resist classical computers, what a quantum machine really does differently, and where the field actually stands today. Along the way, we will correct the most common misconception in the entire subject: the idea that a quantum computer simply tries every answer at once. The concepts may feel unfamiliar at first, and that is completely fine. We will build them up one step at a time. Modern classical computers are extraordinary machines, and for the overwhelming majority of tasks, they remain the right tool. But a few problem classes scale so badly that no amount of engineering rescues them. Consider n interacting two-level quantum particles, for example, electron spins in a molecule. The state needs one complex amplitude for every configuration, so the count is 2 to the power n10 particles need 16 kilobytes, 30 need 17 gigabytes, 50 need about 18 petabytes, and 300 need more entries than there are atoms in the observable universe. Note the wording carefully. This ceiling applies to exact simulation, not to approximate methods. A second hard problem comes from cryptography. Multiplying two large primes is fast, but recovering those primes from the product is, as far as we know, hard. The best-known general classical method is the general number field sieve, and public key systems such as RSA rest on exactly that asymmetry. Note the hedge on the left. Nobody has proven that factoring is hard. It is a well-tested belief, not a theorem. You will also hear that quantum computing is needed because Moore's law is ending. That is context, not the argument. Doubling the hardware speed buys you exactly one more particle. In 1982, Richard Feynman published a paper titled Simulating Physics with Computers in the International Journal of Theoretical Physics. He asked what now reads as the founding question of the field. If nature is quantum mechanical, and simulating quantum mechanics on a classical machine costs exponentially much, why not build a simulator that is itself quantum mechanical? The insight is elegant. A quantum system tracks its own amplitudes for free, simply by existing. This is why quantum simulation of molecules, catalysts, superconductors, and magnetic materials is widely regarded as the most natural application, and the one where a clear advantage is most plausible. Here is the most important correction in this chapter. The popular story says that a classical bit is 0 or 1. A qubit can be both at once, so n qubits explore all 2 to the n possibilities simultaneously, and the answer pops out. This picture is wrong, and believing it makes every real algorithm look mysterious. The machine can indeed occupy a state involving all those configurations, but you cannot read that state out. Measurement returns exactly one outcome, a single bit string chosen at random, and everything else is destroyed. The Halivo bound, proved in 1973, says n qubits deliver at most n classical bits. So what actually happens? The real mechanism is interference. Amplitudes are complex numbers, so they carry a sign and a phase, and that is what allows them to cancel. A quantum algorithm is a carefully choreographed sequence of operations that arranges for the amplitudes of wrong answers to cancel each other out, while the amplitudes of right answers add up. Only then does measurement become useful, because the probability of landing on the right answer has been amplified. This is also why quantum algorithms are rare and hard to invent. Spreading out is easy. Engineering the cancellation is the difficult part, and it needs exploitable structure. This table sets expectations honestly. Factoring and discrete logarithm move from sub-exponential to polynomial with Shor's algorithm, an exponential scale gain that depends on structure. Simulating quantum systems is the most natural fit. Unstructured search over n items goes from order n to order square root of n with Grover's algorithm, a quadratic gain that has been proven optimal, and a quadratic gain can be eaten by slower clock speeds and error correction overhead. Sorting, arithmetic, and most databases gain nothing at all. And crucially, quantum computers are not believed to solve NP-complete problems efficiently. Anyone promising otherwise is exceeding the theory. The field has a clear lineage. 1982, Feynman poses the question. 1985, David Deutsch defines the universal quantum computer, turning that idea into a model as precise as the classical Turing machine, so that there is finally something to write algorithms for. 1994, Peter Shor gives a polynomial time factoring algorithm, and the field acquires urgency. 1996, Love Grover gives the quadratic search speedup. Then the first small devices appear, using nuclear magnetic resonance. In 2001, a 7-qubit experiment factored the number 15, with the answer known in advance. In 2019, a team at Google reported an experiment on a 53-qubit superconducting processor named Sycamore. It sampled from the output distribution of a random quantum circuit in roughly 200 seconds, and the team estimated that the leading classical supercomputer would need on the order of 10,000 years. Now read the right-hand column. Researchers at IBM argued the same sampling could be done in days using disk storage, and tensor network methods reduced the classical cost much further. The task was chosen to be hard, not useful. Always check what the classical baseline was. Today we live in what John Preskill named the NISQ era in 2018, noisy intermediate-scale quantum. Devices have enough qubits to be awkward for classical simulation, but lack the error correction needed for long computations. The central obstacle is decoherence. A qubit interacts with stray fields, vibrations, and thermal noise, and since interference is the whole mechanism, noise erodes the machine itself. The accepted answer is quantum error correction, spreading one logical qubit across many physical ones, with estimates for breaking RSA 2048 running into millions of physical qubits. Several hardware platforms compete, and which will win is genuinely unclear. Let's recap. Certain problems, above all the exact simulation of quantum systems, cost classical computers an amount of work that grows exponentially, and faster hardware does not change that shape. Feynman's 1982 argument was to let physics do the bookkeeping. A quantum computer does not try all answers in parallel, because measurement returns only one outcome. The real mechanism is interference, and it only works for problems with exploitable structure. We traced Deutsch, Shor, and Grover, read the 2019 sampling experiment carefully, and placed today's hardware in the NISQ era. Next, qubits, superposition, and entanglement.